For Roman numeral 3, we're going to look at rotational dynamics. So we've looked at the analogy to go from linear to rotational motion. We've had kinematics, and now we're going to apply that rotational motion to dynamics, which means we will be dealing with forces. So think back in your notes to Newton's laws. You may want to pull those out for this chapter to help you study. The first thing we need to do before we revisit Newton's laws is to define a couple of new terms. The first of those will be moment of inertia. So just like objects tend to resist a change in their motion or inertia, rotating objects also tend to resist a change in their motion. And we call this rotational inertia. It's also called moment of inertia. And what this is an expression for the rotation of a mass in terms of its radius. So that means that it depends on the amount and the distribution of mass. I'm going to circle this statement because that's really important when we deal with moment of inertia. So it's not just the amount of mass that something has, it's also how that mass is distributed, or in other words, how spread out is it away from the axis. Now, when we use moment of inertia in an equation, it will have the variable of a capital I, and its units will be kilograms times meters squared. For this last little part, this tells you how you can calculate the moment of inertia for an object. For us, typically the moment of inertia will be provided for you. However, if there's a situation where you are asked to calculate a moment of inertia based on the object's amount of mass and its radius or distribution, you would use this formula. We would simply take k, which is some fraction that you would be given, times the mass times the radius squared. I know in one of your quest problems for sure, the particular shape object that you will be dealing with, that k value would be a fraction of 1/2. So I'm just going to leave you a little note that one of your quest problems is going to need that formula. But again, typically, and on your test, I will try to provide the moment of inertia already calculated for you. The next thing we're going to look at is torque. And just like our other angular or rotational quantities, this one also gets a Greek letter. It's the Greek letter tau. And you can write it like this, where it's kind of a curvy T, or I've also seen it written like this, where that top part has a loop on the T. Either one, whatever's easier for you to draw. But a torque, what makes this special is that it is a twisting force. So it's our angular counterpart to force. And torque is defined as the force that is applied tangent to the circle rotation around a specific point of rotation. Now I know that kind of seems a little abstract to you, but imagine that we had a circle and we wanted to make it spin around. In order to do that, I would have to apply some sort of force in this direction, and that would make it start rotating like this. So that force that I applied, and then it's a certain distance away from the center, which would be my radius. If I multiply that force and radius together, that's what my torque is going to be equal to. Now I know I use the term radius, but if we talk about that in terms of the displacement from a point of rotation, that's going to be something that's important because I could have applied a force in the middle instead of on the edge. What we're going to do is look at an example of unscrewing a bolt without a wrench. That's really, really difficult to do. But the purpose of having that wrench, like when we talked about our simple machines, that acts as a lever, remember? So that extra distance away from the point of rotation is going to give us extra leverage because it was a lever. And thus, we're going to call that distance wherever we apply our force from the center out to where it's applied will now be called the lever arm. So another definition for you. The lever arm is the distance from the axis of rotation to where the force is applied, and it is really similar to a radius. I know you have this picture in your notes. The force that we apply has to be perpendicular to that displacement or that lever arm. And therefore, if you happen to have a force given at an angle, you would use the sine of that angle to give us that perpendicular requirement. For us, most of the time, you're probably never going to see an angle, so I wouldn't worry about that too much. That's going to mean that our formula is mostly going to reduce down to the torque is equal to the force times the lever arm. And an R is used because it is so similar to a radius. Again, we need to talk about direction. So remember, if we had something moving linearly, we could describe the direction of motion with plus and minus signs, a positive and a negative direction. So we're going to do the same thing. Counterclockwise, remember that's where it goes opposite to the way a clock moves, is considered positive and out of the page. I will talk to you in class about what this term means later. For now, let's move on to clockwise. So that would be the way a clock rotates. That is going to be considered our negative direction. It is also called into the page, but again, we'll go over that in class and talk about what those two terms mean. Now that we have a rotational or angular counterpart to force, we can revisit some of Newton's laws. So today we're going to cover Newton's first law. Remember from last semester, Newton's first law stated if the net force was 0, then the acceleration was 0. So what we're going to do is for rotational motion, replace those terms with their counterparts. So force is replaced with torque, acceleration is replaced with angular acceleration. So we simply rewrite Newton's first law in terms of rotational motion and say if the net torque is 0, then the angular acceleration is 0. As for this bicycle wheel example, we will be doing this as a demonstration in class, so make sure you remind me to go over that and that everyone gets a chance to turn the bicycle wheel. That way you'll be able to feel in person what a torque is like. So now when we apply this idea of Newton's first law, if an object is at rest, it is said to be in a state of static equilibrium. For us, that means that it's not going to be rotating. So in other words, all of the forces cancel out so that the net force is equal to 0. In terms of that rotation, all of our torques would cancel out as well, and the object will not rotate. So we can write that as, remember from chapter 1, that sigma was the sum of, so we would take all of our torques that go clockwise and add them together, and then all of our torques that go counterclockwise and add them together, and those totals have to equal each other. So let's try an example problem. Before we start, I know in your notes you have a lot of a page left. I'm going to do an extra example problem when we get through with this one, so be sure to leave a little bit of room at the end of this page in your notes for us. Thanks. Okay, for this problem, we have a lever, the fulcrum is the pivot point, and there is a giant seesaw. We are going to place a 4,600 kilogram elephant on one end and a little teeny weeny mouse that's only 0.025 kilograms on the other side. We know that the elephant is 10 meters from the point of rotation from the fulcrum, and we want to know how far out we're going to have to place that mouse so that the seesaw will not rotate in one way or the other. That means that the system will exist in a state of static equilibrium. Remember, for our torque, we're going to multiply the force times the lever arm, and then we're going to do that on both sides to show how the torques will equal out, and we can find that lever arm for the mouse. So again, torque is force times lever arm. We have a 90-degree angle from our picture, so we don't have to worry about the sine of 90 because that's just equal to 1. So we are going to say the sum of our counterclockwise torques will be equal to the sum of our clockwise torques. Well, we only have one on each side, so that's going to simplify things a bit. For our subscripts, we have the elephant's force times the elephant's lever arm on one side, and then the mouse's force times the mouse's lever arm on the other side. You should know by now that if you're given a mass and you are asked to find the force, that is going to be the weight of the object, and we would find that simply by multiplying mass times the acceleration due to gravity. So let's make those substitutions. Now we have mass times gravity for the elephant to get its weight or force times its lever arm, and then mass times gravity for the mouse to get its weight, and then times its lever arm. So at this point, we can substitute in the numbers that we know. The elephant was 4,600 kilograms, gravity is 9.8, and the elephant was placed 10 meters from the fulcrum. On the other side, the mouse has a smaller mass of 0.025 kilograms times 9.8, and then we're looking for its lever arm. So how far out from the fulcrum does the mouse need to be? If you were to plug in your numbers, you should get a value of about 1.84 times 10 to the 6 meters. This would be the equivalent, just to give you a reference, of a little over 1,400 miles. That's not exactly practical, but it would show us how far out that mouse would need to be in order to balance out that elephant. Now, I know that was an extreme example, so we are going to have other examples to kind of balance this out and make the scenario a little bit more practical. Now, I did pose this question to you. Can you think of anything we forgot to include in that last example? Remember, in that last example, we had the elephant 10 meters out, and then that little teeny mouse way, way, way far out, 10 to the 6th meters away. Perhaps you can recognize that all of this part of our lever would actually apply and have a weight to it that would be pulling down as well. So this would mean that if we have a fulcrum that is off center, we would actually need to include the plank or the lever itself in our equation. Now, I won't walk you through all of the steps, but I do want you to recognize that if your fulcrum is off center, we would need to take into account the force and the lever arm of that lever itself, which I've done right here. For the most part on our examples, we are going to have a fulcrum that will be exactly in the middle of our lever, so you won't have to worry about this extra torque being applied, but I do want you to recognize that it is possible to have more than one torque on one side in order to put something in equilibrium. So let's do that more simple example. Hopefully you left room in your notes and we can try one together. So I've made up this problem for you. We have a 245 Newton child and her 75 kilogram babysitter playing on a seesaw at the park. The child is going to sit 1.8 meters from the center of the seesaw, and you're asked to find how far away from the center should the babysitter sit in order to balance the seesaw. I find it helpful to draw a picture to kind of visualize the situation. So we know that the child is going to be sitting 1.8 meters out from the center, and we don't know how far the babysitter should sit, so that's what we're going to be looking for. Remember, for them to balance, we want to balance out our torques, so we're going to say the torque on the left-hand side or the counterclockwise side will equal the sum of the torques on the clockwise or the right-hand side. We only have one torque on each side since our seesaw is balanced, so that's going to make things easier. I'm going to say the force of the child times the lever arm of the child will equal the force of the babysitter times the lever arm of the babysitter. Now, we were given a force of the child. Do you have a force of the babysitter? No, not really, but you can find it. So remember, you're given a mass. We're going to change mass to weight to get that force number 2. So go ahead and try that. I came up with a force of 735 for the babysitter. So let's plug in our numbers. Over here, we know that the child has a force of 245 newtons and a lever arm of 1.8 meters. And then we found the weight or the force of the babysitter, which was 735 newtons, and we will be looking for that second lever arm. Go ahead and pause the video and solve for the second lever arm. You should get an answer of 0.6 meters. This will typically be more like the problems that you're going to see in our quest problems and definitely in our lab. You are going to use a meter stick and hang masses on both ends at different lever arms to see where you need to balance those torques. That's it for today, and I look forward to our next lesson.